Dr. Shamila, all lecturers from RPG community, and my fellow friends. Today I'll be presenting vectors in navigation. My name is Yuan. Introduction to vectors, a mathematical quantity with both magnitude and direction. Unlike scalar quantities, temperature, mass, or something else, vectors describe directional movement. Examples: velocity, force, displacement, and acceleration. Components represented using I, J, K along coordinate axes. Operations: addition, subtraction, magnitude calculation. Application: navigation, physics, and engineering. Application of vectors in navigation field. Ship movement is influenced by multiple vectors quantities acting simultaneously. First is ship velocity, direction and speed generated by engine. Second is current velocity, water movement affecting ship motion. Third is resultant velocity, actual movement relative to Earth. To analyzing vectors, navigators predict displacement and adjust direction to reach intended destinations accurately. Vector calculations in navigation. Scenario: delivery drone operating in 3D space experience two velocity vectors simultaneously. Vector A is propulsion velocity. A equals to 2I minus j plus 2k. Vector B is wind disturbance. B equals to I plus 2j minus 2k. Vector addition is R equals to A plus B. And calculate resultant R equals to 3I plus j. Determine motion is actual direction of movement. To maintain flight stability, drone controller adjusts force by increasing propulsion and reversing disturbance. The original vectors is A equals to 2I minus j plus 2k, B equals to I plus 2j minus 2k. The adjustment applied R equals to 3A minus 2B, and the new resultant is R equals to 4I minus 7j plus 10k. This demonstrates how vector mathematics counteract environmental disturbance to maintain intended flight path. Magnitude and direction analysis. Magnitude calculation is modulus A equals to square root 2 square plus negative 1 square plus 2 square. The answer is 3. Unit vector is A equals to 1 over 3 times 2I minus j plus k. Angle between vectors, the answer is 116.4 degrees. It is greater than 90 and shows opposition. Magnitude of A is 3. Propulsion force strength is shown. Dot product analysis reveals vectors oppose each other, explaining why environmental disturbance reduces propulsion efficiency. Application of mathematical tools in real-life situations. Mathematical tools bridge theoretical concepts and practical application, enabling us to interpret and control the world with precision. First is quantification, converting real-world phenomena into structured, measurable datasets. Second is modeling, creating robust mathematical representations to simulate complex systems. Analysis, interpreting interactions and relationships between dynamic environments. Prediction, forecasting future outcomes by extrapolating from known variables. Optimization, identifying the most efficient solutions under specific constraints. These principles are vital for navigation systems like GPS and aircraft autopilot. They ensure the accuracy and reliability required for safe, high-stakes decision-making. Mathematics in decision-making. Vector analysis supports critical decisions when environmental forces influence movement. The problem is ship experiences eastward current while traveling north. The solution is still 14.04 degrees west of north to compensate for drift. Outcome is minimize fuel consumption, reduce travel time, improve safety. Vector calculations determine optimal steering direction, transforming intuitive judgment into structured, evidence-based decision-making. Importance of mathematics in solving real-life challenges. Mathematics acts as a universal language for problem-solving, providing the essential framework to model and address challenges across diverse fields. Accuracy, it provides precise interpretations of complex phenomena by revealing underlying quantitative truths. Optimization, it identifies efficient solutions by evaluating parameters and trade-offs under constraints. Reliability, rigorous logic ensures consistent and dependable results that system can trust. Universality, principles apply across all disciplines, ensuring a unified approach to global problems. Scalability, mathematical models scale seamlessly from daily tasks to massive global systems. Predictability, defining variable relationships enables effective forecasting and proactive risk management. Mathematics is an indispensable tool that transforms chaotic real-world variables into structured, solvable components to drive human progress. Conclusion, vectors are indispensable tools for modern navigation, enabling the precise analysis of motion influenced by multiple forces, as demonstrated in our drone navigation case study. Operations such as vector addition, magnitude calculation, and dot product analysis are critical for determining resultant motion, evaluating force interactions, and predicting displacement. Furthermore, mathematical modeling allows for the systematic interpretation of complex navigation scenarios, while vector analysis facilitates effective decision-making by identifying optimal solutions under environmental constraints. Together, these frameworks provide a powerful evidence-based approach to addressing real-life challenges in diverse navigation contexts. Vector algebra transforms intuitive judgment into structured and evidence-based decision-making, allowing engineers and navigators to manage complex situations effectively.